Thanks for joining me today, everybody. As Chris said, I am an engineering manager at a small software company in San Francisco called OneSignal. We're a omni-channel messaging company, so our customers are website builders, app builders who want to send messages to their user base using push notifications, email, in-app messages, etc. So this is kind of a bug retrospective, so we need to sort of jump back in time a little bit so I can set the stage for you and talk about what's going to happen here. So at this time, we were sending around 8 billion push notifications every day. We had about 10 engineers working on our backend team who were managing all the systems that did this. And when you're operating at that like sort of large-ish scale with that kind of small-ish number of engineers, you have to make a lot of concessions in the name of performance and meeting the goals that you would like to make, right? So the problem that we are trying to solve today is we are fronting the API that updates data properties for our customers' subscriptions. So our customers are going to be sending us HTTP requests like this that correspond with a single app, which is like a single customer's data set, and a subscription, which is a single device. So we allow customers to store key value pairs, arbitrary key value pairs associated with all their subscriptions. In this case, we have John Smith in there as a customer's name. So this would allow our customer to do something like, hi, John, please come back to the app and check out this great sale that we have right now. So a single person might have multiple subscriptions associated with them. They might have multiple subscriptions on a single device, like a mobile push subscription as well as an SMS subscription. And then in a different device on a web browser, they might have a web push subscription. And these would all be stored under different records in our database because our data storage model was, at this time, very device-centric. Yeah, so you can see all these records have independent storage for this account type key value pair on them. We started out with a pretty simple API. It was just a REST server that was sending updates directly into Postgres, and that worked for a time. But then we started to get to a certain scale of user base that when we got to like the hour and the half-hour marks, we were just getting hammered with tons of traffic because everybody loves to schedule all their stuff to happen at hour and half-hour marks. Nobody's scheduling stuff to happen at 11:02 in the morning, right? So we started to get hammered on our Postgres updates. We started to get a bunch of CPU utilization, lock contention on rows, things like this. So what were we going to do with these updates? We decided to stick them in a queue because queues are a lot easier to control, right? Queues, just like the queue you wait in at the cafe, you in-queue stuff at one end, you de-queue stuff at the other end when it's ready to be processed. When we had this variability in the in-queue rate at the hour and half-hour marks, we were able to keep the de-queue rate the same. So instead of saturating our Postgres connections and taking our servers down, we just built up a little bit of lag. So our updates were slightly delayed. We could deal with a 5-minute delay in updates. That's preferable to knocking out our web servers, knocking out our Postgres servers, right? But in the real world, we don't use just a queue, right? We use real implementations of the abstract data structure of a queue. And in our case, we're using Apache Kafka to queue these updates. So this is an event streaming platform. It's very widely used. And yeah, so the way Kafka works, more or less, we have a queue, we have a topic, which is like a logical grouping of messages. Messages all have incrementing IDs, which are called offsets. In this case, we have offsets 0, 1, 2, 3, and 4. Messages are added onto the topic by a process called a producer. They are pulled off of the topic by a process called a consumer. And the way that Kafka keeps track of where you are in the queue is not by mutating the queue, but it's by actually just changing which offset you're currently looking at. So it's just sort of a pointer to that queue of messages. And then when we're done processing a message, you send Kafka a commit, which will change which pointer you're currently pointing to. And this is very convenient because it means that you can actually have multiple consumers, which are all consuming from the exact same queue. So in our case, we're fronting basically Postgres writes, we started out by fronting Postgres writes to update these user properties, right? But at a certain point, we realized that, oh, these user property updates could actually be useful in a bunch of different product areas for us. So we actually have many different Kafka consumers which are reading from this same user property update stream. And we use that to sort of feed the data intake for many of our different features. And that's basically only possible because Kafka is storing just a pointer in there for each one of the consumer groups. Yes, and then if you want to scale Kafka horizontally, because we all love to scale horizontally, we do that using something called a partition. So each Kafka topic is divided up into numbered partitions, and these each have independent numbering for all of the offsets of messages in there. So in this case, we can see that partition 0 is currently looking at, oh, that number is wrong, I'm sorry. Partition 0 is currently looking at message number 1, and partition 1 is currently processing message with the offset number 2. So something that's sort of relevant to us that I touched on briefly was latency, the number of messages that are sitting in Kafka and waiting to be processed, right? So in this case, partition 0 is going to have 4 messages in lag, in latency. It's got 1, 2, 3, and 4 on it. And partition 1 just has a single message in lag, right? Yeah. And there's a couple of ways that you can distribute messages to the different Kafka partitions that you have. You can do that. You can basically let Kafka do this for you. If you just have your producer dump the message into Kafka, it will sort of round robin messages between all the partitions. And that might be OK for you. It might not be OK. But in our case, we were fronting Postgres writes. And these Postgres writes were going to one of several servers inside of a large cluster of Postgres servers. And the sharding scheme for those Postgres servers was consistent. It was based on the sort of the app ID, which is like the customer dataset ID. And so we actually would not use that round robin method. We were doing explicit assignment of messages to different Kafka partitions. So at the time we were producing the message into Kafka, we would say, all right, this is going to which data set? All right, dump it into this partition. So each partition was going to have messages for only one Postgres server in it. This meant that if one Postgres server had an availability issue, it would not spread to sort of other Postgres servers. So we wanted to try and keep our blast radius for Postgres downtime as small as possible. It also meant that if one app was spamming us with a lot of updates, hopefully that isn't going to be causing latency issues for us across multiple partitions. The other nice thing about this is it allows us to pretty easily control the concurrency on Postgres writes. So if we had, say, 2 Postgres servers and we wanted to perform 2 concurrent writes to our Postgres servers, we could create a Kafka topic which had 4 partitions and have each of those partitions performing a write to one of the Postgres servers. So in this case, we have 2 partitions which are sending writes to the red server and 2 partitions which are sending writes to the green server. And this got us pretty far. We used this for a while, and it worked pretty well. But the numbers always keep going up, and so you have to get creative as time goes on. And we started to run into a couple of problems with this. At the times that we wanted to control the concurrency a little bit more finely grained, right? We wanted to increase the number of concurrent writes that we're performing to Postgres. This system started to show itself as pretty inflexible, because if you wanted to, say, go from 2 concurrent Postgres writes to 3, the way that you would accomplish that was by doing a repartitioning of Kafka. And if you have ever been a part of that process, it's mildly annoying and time-consuming. So the way that you do this, basically, is to create a new topic, which has the desired number of partitions, and you dump all the messages from the old topic into the new topic, and then you shift your producers over from the old topic to the new topic. And if you care about which partition a message is assigned to, that producer cutover is quite annoying as well. And if you care about the ordering between the old messages and the newly produced messages, then you need to get even more so creative with it. And you may trying to introduce this in a way that also doesn't contribute massively to a bunch of lag in Kafka is quite frustrating. So this is the thing that we wanted to sort of architect our way out of having to solve all the time, because what if we get better CPUs on our database servers? What if we decide that we want to prioritize reads over writes, and we're okay with a little bit more latency on this topic? We wanted to be able to be more flexible and not be quite so constrained on having to care about our Kafka partitioning scheme. So the way that we accomplished this was something that we called subpartition processing. So inside of a Kafka partition, right, basically doing concurrent processing of individual messages. Normally, the Kafka folks say, don't do that, but we did it anyways. So what does this look like? So we have a number of workers, a number of processors that are a part of each partition, and each of those can process a message concurrently. Because they're all associated with the same underlying Kafka queue, this means that we can control the number of workers very easily. It's just a number in a config file, and we can change this by just redeploying the consumer. And if we wanted to be really dynamic about it, we could even make this a property that was able to be live updated. Yeah, so this got us even further. However, this in and of itself introduces another problem that we need to solve. So if you're processing messages concurrently, you're going to eventually process some messages out of order, right? So if we have messages with offsets 0, 1, 2, and 3, what happens if messages 0 and 3 are completed at around the same time? Under the normal semantics of a Kafka consumer, you do a commit after a message is processed. So when we perform the commit for message 0, that's fine, because Kafka is like a linear log of messages, right? So when we commit 0, that's fine, because it's at the beginning of the topic. But when we run the commit for the message with offset 3, this presents a problem, because Kafka does not store like each message's commit status. Yes, this was committed. No, this wasn't committed. It only stores for each consumer group and each partition the last message which was committed, or the greatest offset that was committed. So that means when we send a commit for the offset 3, it assumes that 1 and 2 were also completed and also committed. Now these messages are still being processed inside the consumer, so they're really not completed. And it's okay for the sort of interim time period where these messages are still being processed, but if the consumer was to get a rebalance, or if it was to be restarted by Kubernetes or something like that, we're going to run into a problem, right? Because then these messages might never end up being completed, and we don't really want to drop anybody's Postgres writes on the floor. So how do we solve this? The solution that we came up with was to use something called a commit buffer. So instead of sending the offsets of completed messages directly to Kafka, we instead dumped them in memory into this data structure, which was storing, is the message completed, yes, no. And after doing this, we would scan from the beginning of the commit buffer down, and we would check to see if there was a contiguous block of completed messages starting at the beginning, right? So in this case, we do have a contiguous block just containing one message, right? Just message with offset 0. So we would go ahead and send that commit to Kafka, just the message with offset 0. So 1 and 2 are now at the front of that block. We sort of re-index, we shift the block up. 1 and 2 are now at the front, and those are not completed. So we can't do any more commits. So message 3 is just going to sort of sit there in that commit buffer, waiting for that block to finish before it can move on. And at a certain point in time, the messages with offsets 1 and 2 are going to be completed, right? And at this point, we are going to have a contiguous block of messages from 1, 2, and 3. So we can then send Kafka a commit for the message with offset 3. And it now correctly knows that messages 0 through 3 are completed. So once again, this bought us another layer of stability and another layer of performance gains, right? But we started to run into problems with this as well. this has a big concession with it, which is you are getting at least once delivery, at least once delivery. There's a number of sort of models that Kafka consumers operate on. There's at least once delivery. There's at most once delivery, where a message might not be read at all, but it's not going to be read more than once. And there is exactly once delivery, which is basically just a big bucket that you pour money into. And your time is much better spent writing a document about why you actually don't need exactly once delivery, or why you should pick something that isn't Kafka. So we're doing at least once delivery. This means messages at a certain point are probably going to be replayed. And so you have to sort of design your system around this. You have to either decide that it's OK if values are inconsistent, or you have to design a way that your system is not going to do that right a second time. I'm not going to delve too much into how we designed our system around this, but I can answer questions about it later if that's desired. Yeah, so let's talk about what we've got so far, right? We have a Kafka topic, which is composed of multiple partitions, and these are independent queues of messages. Each message has an incrementing offset starting at 0 and going up. We have a producer that enqueues messages into the topic, and we have a consumer which dequeues messages out of the topic. We can control the concurrency of that consumer using the number of Kafka partitions, as well as the number of subpartition workers. And then this particular consumer, in this case, is performing Postgres writes. Yes, let's talk about these Postgres writes for a moment. What happens if we perform 2 concurrent Postgres writes, which are targeting the same row, right? What happens if a customer rapidly sends us 2 update requests, one to set a property to 10, and another one to set the same property to 20? If we're processing those 2 updates concurrently, we might at some point process the message that the customer technically sent us second before the one that they sent us first, right? So we might, in Postgres, set the property to 20, and then a short time later, set the property to 10. Maybe this is acceptable, but we decided that we can't intuit what the customer wanted, so sort of the best thing we could do in this strange situation was maintain the ordering guarantees that the customer provided to us. So we decided that this was not acceptable. We didn't want to process updates for the same row concurrently. We wanted to maintain the same ordering that the customer provided to us. And the way we did this, we identified a couple goals of this process, right? We wanted to maximize concurrency. We wanted to saturate our Postgres connections up to the limits that we had defined, do as many operations as possible concurrently, while minimizing contention for individual rows and never performing concurrent updates on a single row, right? So the way that we accomplished this was with another layer of queuing, because it's queues all the way down, I'm afraid. So we did this using something that we called subpartition queuing. So we have a partition that is a real queue that Kafka maintains. And what we did was we took the subscription ID, which is the ID of the individual device, and we hashed that, and we used it to put it into a queue that was feeding into one of the processors, into one of the workers. So these queues are matched one-to-one with the workers, and because which queue we're assigning to is computed as a hash of the subscription ID, which is a row ID, we're never going to process updates for a single row at the same time. So assuming that the number of updates that we're getting is distributed across all of our rows in the database, we're going to have queues that are processing messages concurrently, but those updates are never going to be for the same Postgres row. So if we put all of this together and look at what one of our Kafka consumers looks like, right? We have a producer that's dumping messages into Kafka and it's picking a partition based on the ID of the application, the customer's data set. Kafka is storing those messages. It's being pulled off by a consumer that consumer is distributing the messages to an in-memory queue based on the row ID. We have a commit buffer that's storing the in-process commits, and then everything is going to Postgres eventually. And suddenly, for a sec, everything was fine. And we got on for like a really long time without any major problems in this system. But when everything is fine for a while, usually at a certain point, it ceases to become fine. And that's what I really want to talk about today, is the point where it stopped being fine, right? So we started to get paged on huge spikes in message latency in our consumers, right? So we're talking about like latency going from maybe 5,000 messages at a time as like our base rate to tens of millions of messages at these peaks. And we really had a tough time figuring out why. We did notice that the latency was not associated with a single partition. It wasn't associated with all partitions. It was smeared across all of the partitions which were assigned to like a single consumer instance. It's like one of our Kubernetes pods had all of its partitions that were lagging. So we looked at the stats for this one pod, right? We expected to see elevated CPU usage. We expected to see every Postgres connection checked out of the pool and performing writes as quickly as possible. And what we actually saw was the complete opposite of that, right? We saw CPU usage at nearly 0, and we saw every single Postgres connection except one sitting in our connection pool doing nothing. So we're like, okay, there's a virtually infinite amount of work that you could be doing right now, but you're just sitting there doing nothing. It's just like me. It's just like me. Okay. So we're like, what is happening right now? What's going on? So we tried to answer this question using the observability tools that we had available to us, which at this time, unfortunately, was basically just metrics. Now, metrics are great. They can get you very far. You can build great alerts off metrics, but they're pretty limited when you're trying to like debug something that's going wrong in production, right? We did have logs, but they were scattered. They were like physically on the boxes. They were unstructured. We had no centralized, no structured logs whatsoever. This is something that I was like trying to get implemented at the company sort of since I joined, because I came from a much larger company that had a great practice of centralized structured logging. And I joined the team and I was like, all right, great, where do I go to see the logs? You SSH onto the box. No, I don't do that. So at this point, when we're dealing with this problem, I'm like, all right, we need to get better observability in place to solve this problem, right? So I use this as like a jumping off point for getting centralized logging, centralized observability set up. So we had all of our consumers now dumping structured logs into a centralized logging provider, and we were able to then do some analytics based on that. Now, we weren't sending a lot of information for each event, but all of our events were sending, which app ID, which customer data set, which subscription ID, which is like the Postgres row, the SQL that we were using, sending to Postgres, and the host name of the consumer instance, right? And the first thing we did was like, all right, let's group this by the data set. Let's group this by the app ID. And we immediately noticed something very striking. We noticed that of the small amount of updates that were being performed, nearly all of them were associated with a single customer data set, which we're going to call Clothesly, which is not a real website. So if Clothesly was doing maybe 500 updates per second, the next largest customer was maybe doing 5, and all other customers together on that one pod were doing maybe 30. So just enormous gap in the scale here. And we were, remember, at this time sending like 8 billion push notifications per day. Our SDKs are in something like 9 million mobile apps. So for one customer to be dominating like one of our boxes, that indicated that something was pretty wrong. And since we had it available to us, we also grouped by the subscription ID, the row ID, right? And then we noticed something really strange. Most of the updates were going not just to Clothesly as a data set. They're actually going to a single subscription, a single device in Clothesly's data set. And they had around 5 million devices. So a data set of 5 million devices in our entire database of billions of devices, and we noticed one of them as causing problems for us. So this was very surprising to us. We're like, why is this one device showing up? Why do I care about it? So we started looking at what updates were happening, right? We could have just grabbed the subscription ID and disabled updates to this one device and moved on and said they're doing something weird and we don't care, moving on. But we wanted to figure out what was happening with this app so we could try and prevent it from happening with our other customers, right? We looked at the updates that we're sending to this one record, and it was tons of updates to individual fields, and these updates seemed to be incompatible with each other, right? So the same field was being constantly reset to very, very different values. Things like the location record was moving like Chicago to Tokyo to San Francisco to Brisbane. It was very very confusing, and we knew that the customer must be doing something very wrong in their SDKs, but we really wanted to try and understand what it was. So we looked at the row in Postgres, right, and we were just constantly spamming select star from this row to try and see what's happening in these fields. We noticed that basically every field was changing constantly, but there were a couple fields that maintained consistency. It was always marked as an email device type, and the identifier, which is the way that we actually contact the device. So for a push device, this is the token we get from Apple or Google or whoever. But for an email record, it's just the email that we use to send out. The identifier was always set to admin@Clothesly. And this started setting off alarm bells for us. It started to sort of click into place, and let me explain why. So OneSignal started as a push notification company, so a lot of the stuff that we have is very centric around push notifications and the device and the SDK, right? But we started branching out from there. We tried to be more than just push notifications, and we're trying to let people do omni-channel messaging to their customers because it's very cool and in word right now. And the first platform that we added that wasn't just push was email. And the way that we let our customers access this was through a method in the SDKs called setEmail. And when you called the setEmail method, you provided it with an email address. And what it would do is it would send a request to our servers that would either look up or create, if it didn't exist, an email record with a given email address. And then it would link the push notification record that's associated with that SDK install to the email record by setting a property on the push record to point to the email record. And then it's going to store that, the email subscription also in the SDK. And every time the SDK issues an update of a property, it's going to send a duplicate update that's associated with the email subscription. So we checked this parent property. We checked to see, okay, how many subscriptions does Clothesly have? They have around 5 million subscriptions. And how many of those subscriptions have their parent property set to this one admin@Clothesly record? It was almost every single one of them, right? Almost every single one of them. So what does this mean? It means that on every single SDK install that they had a line that just said set email admin@Clothesly, right? So they probably misunderstood our docs. They probably thought you were supposed to call set email with an email of the administrators of the app that OneSignal could use to contact you if there was a problem or something, right? It's kind of an understandable misunderstanding to make, but it was not one that we had ever thought somebody would do, right? So yeah, they just had a ton of records, which were all linked to this one central email record. So why is this really a problem? Why do we care? Why am I talking about it, right? We have a Kafka queue. that's full of a lot of updates for this one individual subscription, this one individual row in Postgres, right? How does that translate into, basically all of our concurrency going to nil? Why is this a problem? Imagine for a moment that we have our 3 subpartition workers, and they have a basically fair distribution of messages on them. They're all going to the different queues, and as messages are completed on one queue, as say this red message is completed here at the beginning of the queue, we can shift all the queues forward, grab some more messages, and hydrate the rest of the queues, right? But what happens if we put our thumb on the scale, kind of like Closely did here? What if we have a ton of updates that are just going to one subscription, right? They're all going to be hashing to the same value. They're all going to wind up on the same queue, right? So this means that the other subpartition queues that we have are going to be pretty dry. There's not going to be a lot of messages in there. So in this case, Q2 up here just has a single message in it, right? When that message is processed, if the message at the beginning of the queue, which is associated with Q0, is not finished processing by then, Q2 is just going to be dry. There's going to be no messages in there, and the worker is not going to have anything to process, right? So this means that your consumer is going to be sitting there, and all of the beautiful workers that you have waiting for more messages to process are not going to have anything to do, and your process rate is going to go way down. And in reality, it was slightly worse than this, because the limit on the number of messages that we would store in memory was applied not at the partition level, but it was actually applied at the consumer level, at the process level. So this meant that as these queues started to back up, this one partition was sort of eating up all of the memory capacity of our consumers. So the rest of the partitions that we had assigned were also having all of their queues run dry. So basically the only thing this one consumer instance was doing was processing updates for this one row. And we had thousands of workers that were associated with this one process, and only one of those workers was really doing anything. So that was not so good. So what did we do? How did we solve this problem immediately, and how did we fix it sort of more broadly long term, right? The initial thing we did was skip these update messages. We're like, all right, if you have this subscription ID, we're throwing your update out. Sorry. This row definitely does not need to know that this email record is constantly having its location changed. That's not relevant. It's not important. And when we did this, the process time for each message went from 20 milliseconds to under 1 millisecond. So that meant we were able to churn through that lag very, very quickly. You're not able, unfortunately, to just delete messages from Kafka. You just have to sort of play them and skip over them. But that's very, very fast. The next thing we did was we fixed the limiting of messages. So we took that global message cap, and we scoped it in to be a per partition message cap. So if this were to happen again in the future, we would not let all of the partitions have their queues run dry. It would just be scoped into a single partition. So we took the sort of blast radius of that problem, and we made it much smaller. And the next thing that we did was we said, OK, how were they able to enter into this situation in the first place? Well, they linked too many records together. So we set limits on how many records you could link together, because we didn't really think it was reasonable to have 5 million subscriptions with the same email address associated with them, right? And what did we learn? What did we sort of take away from this? Users are basically always more creative than engineering and product teams, right? They will find really fun and interesting ways to misuse your system that you never considered in the past. So the best you can sort of do is put limits on what the users do. And when you're building those limits, you want to try and scope them in as small as possible, so that a limit in one place isn't going to have a larger effect than intended. And the other thing we gained was the centralized observability, the centralized logging, and the structured logging that we put in place was really instrumental to solving this problem. So if you or your company is interested in sending push notifications and not linking 5 million email addresses to a single user, check out OneSignal. We're at onesignal.com. And if you're interested in contacting myself, all my information is on my website at lilymera.xyz. And I think with that, we have a couple minutes for questions.
Okay, who's got a question?
I think this one over there.
Hi, Lily. Great talk. Thank you.
Thank you.
You mentioned that you had merely, or mostly merely, metrics for observability. Have you built any more observability into your Kafka?
Yes. So after this sort of debacle, I use this as a jumping off point to be like, observability is important and we can't ignore it anymore. So we started off with just structured centralized logging. And then maybe about a year and a half ago, we started investing really heavily in tracing, using OpenTelemetry and sending all of our stuff to Honeycomb. And that has been just a total game changer for us. It's been really instrumental in not just debugging stuff that's causing problems for us in production, but even in the development process as we try and understand how stuff moves through our big distributed system. So yeah, tracing, logs, metrics, all very important.
Thank you very much.
Hi, thanks for the presentation. So you mentioned commit batching.
Sorry, what was that?
You mentioned commit batching to
Yes.
write this to the Postgres database. And you promised to go into the details how you make sure idempotency is maintained if your memory cache fails.
Sure. Yeah, so basically each subscription row in our database also has a field on it called Kafka offset, right? And so every time we write a row, we do one of these update calls. We also set this Kafka offset property to be the offset of the message that's performing that update, right? And then in that call, we have a condition that's the where condition for that call looks like, where app ID equals this, where subscription ID equals that, and Kafka offset is under this value, right? So if we have already played a message for that row that has that offset or has a greater offset, then we're just going to skip it. Okay.
It sounds like you had to build a kind of a contraption around Kafka to make it do what you wanted to do. If you were starting again today, would you start with Kafka or would you do something else with some other system?
That's a good question. That is not something that I've thought about. I think we have developed the system to be pretty robust and very high performance. I think the benefits that we get from Kafka, this talk was mostly about how complicated it is and how smart we are for coming up with this great system. But really, as most talks are, right? But really, Kafka has been quite beneficial for us. One of the key benefits that I sort of briefly touched on was the fact that we can dump all of our updates into one place and then have lots of things that are consuming that same update stream has been really, really beneficial for us, right? So this is powering things like data integrations with third-party providers. It's powering these property updates. It's powering an events-driven drag and drop node programming tool, basically, that our customers can use. So it's really been quite beneficial for us. And we've also had essentially zero operational issues with Kafka itself. They've all just been sort of around our consumers, the things reading off of it, versus something like Postgres, which we also operate at a pretty large scale. That is just constantly on fire and needs like constant hand holding and tuning. So I think the benefits that we've seen from Kafka outweigh the cost that we've paid to use it. Yeah. Other questions?
I have a follow-up question on that.
Yeah.
Early on, you mentioned the mild annoyance of repartitioning your Kafka stream. Does that require you to basically shut down the producers or consumers? And so how long does it take for that kind of operation?
Yeah, so I guess it requires you to shut down consumers for a very brief time. Like you basically just have to redeploy your consumers, right? So you can take your consumers and point them from the old topic to the new topic, and then start up your process that's dumping messages from the old topic into the new topic. So I guess as long as it takes to start that process that's dumping messages from the old topic into the new topic. I don't recall exactly how much downtime was associated with that. Any other questions?
Did your customer ever solve that issue, and what was the impact to them with having all these emails being the same?
I don't know if our support team was ever able to get in contact with them. Yeah, so I don't know if they ever figured out that they were doing something really wrong or not. I think I remember talking to them maybe a month after we discovered this problem, and they said, yeah, we've never been able to get a response from them. So I don't think we ever heard back. We have a large number of customers who are just using our free plan. I don't remember if these guys were paying us or not, but it's fairly common for us to not be able to get in contact with our customers, and we have just huge numbers of customers. Anybody else? Awesome. Well, thank you so much for attending, everybody.